So we've learned so far in our chapter 20 on electrochemistry about the concept of what oxidation and reduction is, how to balance using the half reaction method by keeping tabs of the oxidation numbers, and understanding the guts of a voltaic or galvanic cell, two half cells set up in such a way that the flow of electrons is spontaneous and registers a reading at a voltmeter connected in the external circuit. Now, by definition, if something is being oxidized, something is being reduced. So we also learned that there was a way that you could rank various reduction half reactions as to the strength of their ability to be good reducing agents or good oxidizing agents. So a way to think of that chart is the strongest oxidizers. That means things that cause other things to be oxidized, or the ones that really themselves want to be reduced. Those are going to be found up here in the upper left of this chart. This is just sort of a different representation of the reduction potential chart. And they would have the most positive reduction potentials. And those half reactions that have the most negative reduction potentials, they're the ones that are more likely to be reducing agents. They themselves are going to be oxidized. Let's look at another way to think about that. The more positive your reduction potential is, the stronger that you're going to be as an oxidizing agent. And the more negative your reduction potential is, then the weaker you are as an oxidizing agent. To restate that as another way, if you're a strong oxidizing agent, you have a great desire to be reduced, you have a desire to gain electrons. And then the more negative the value of that reduction potential, the opposite would be true. The more likely that substance would be being being oxidized. So any species that's higher to the left of this table that we're going to take a look at in just a moment will spontaneously oxidize any other species that's lower than it and more over to the right. So take a look at, say, fluorine compared to hydrogen gas or lithium metal. Back here on the chart, fluorine is up here to the upper left, and hydrogen gas and lithium metal are down to the bottom right. So what we just got done saying was that a species that's higher and to the left will spontaneously oxidize anybody who's lower and to the right. Now, usually the reduction potential tables don't look like that. They just have a list from most positive down to most negative. Sometimes other books reverses them. Find a way that your brain can hang on to it. Because what we're going to do is now be able to calculate what are the reactions that are being oxidized or reduced, what are the half reactions that are occurring at the anode and cathode, and be able to predict if a reaction is spontaneous or not. But remember, on any oxidation reduction potential chart, the greater this distance between the reaction that is showing reduction and the reaction that is showing oxidation, then the greater the voltage of that cell is going to be, and the more useful that would be as a reaction to be able to do useful work. Now, if you haven't already gotten out your PowerPoint notes, or if you have a textbook that you can quickly open and follow along with, feel free to make notes, but realize that these are exactly the same as what you see in your textbook. So the first kind of a question you might have at one of the simpler levels is to determine what are the half reactions that are at the electrodes and be able to calculate the cell electromotive force, or what I call the voltage. Remember, we learned that once we determine who is being reduced and who's being oxidized, cathodic minus anodic voltage will give you the voltage or the electromotive force of that cell. So here are two reactions, and they're throwing them out there to you potentially. Who would be more likely to be being reduced, that is, gaining electrons, cadmium ions or tin ions? So you trot to one of those one of those reduction potential charts. And if you go look that up, the one with the more positive value up near the top is the one that is more likely to be being reduced, and therefore that would be happening at the cathode. And the one with the less positive value would be the one that is more likely to be being oxidized, and that would be happening at the anode. So if you really go to this Appendix E, you can use your Zumdahl one or you can use the one in the back of your textbook. You can see that the reduction potential for cadmium is negative 0.403. and the reduction potential for tin is negative 0.136. Now, yes, I know they're both negative numbers. Well, which of those two is more positive? Which one would be more near to the top? And of course, it would be the tin. Less negative means that you're more positive. So the tin must be the one that is being reduced at the cathode, and the cadmium then is the one that is being oxidized at the anode through loss of electrons. And now we just go cathodic voltage minus anodic voltage based upon that reduction potential chart gives us the voltage of the cell. So I'm going to take the cathodic voltage, negative 0.136, and I'm going to subtract negative 0.403, which is essentially adding 0.403 volts to get the cell potential or the voltage of the cell to be 0.267 volts. Now I know this is still bugging some of you, so I'll say it one more time because it can't hurt to hear it too often. Yes, we have a chart that lists them by reduction potentials. Yes, I know it's the anode where oxidation is taking place. So another way to think of this, if you don't like the simplistic cathode minus anode way, you can always in your mind's eye take the cadmium reaction, which is really being oxidized, and flip it over. As soon as you wrote it in the reverse, then the voltage for cadmium would be 0.403. Then you could simply add it to the voltage at the cathode. Please notice that's mathematically exactly the same thing that happened down here. So again, don't let the fact that they're showing the anodic reaction as a reduction. Right now they're just comparing the two to decide which one was the more positive and which one therefore was the cathode. And I think I just went through that. Okay, your next sample exercise, 20.8. Oh, and this was a practice exercise, I believe. And this looks like a rerun slide, so ignore that guy. I don't know how that slipped in there. On 20.8, what we're going to do is simply look at these three ions and rank them in order of their strength as an oxidizing agent. So if you look these up on the table, as written, they're all being shown as reductions, and the voltage is over on the right-hand side, or we call that the reduction potential under standard conditions. Whichever one is the biggest and most positive, that's the strongest oxidizing agent. So I think you can see this is pretty easy. I would rank the dichromate ion as the strongest of the three. The middle strongest one would be the nitrate ion. And then the third one that would be the weakest of the three would be the one that is the 0.8 volts. That would be the silver ion. So here they show them in order of weakest to strongest, and they asked us to rank them in order of increasing strength of oxidizing agents. So that's why it's being shown left to right. Just make sure you always have your little greater or less than signs pointing to the smaller value, and you'll never get mixed up which order to put them in. Now the third kind of problem is asking you to raise up your knowledge or your understanding to a higher level. And there are two reactions here. We're going to break them down step by step. And as written, that's the key thing. As written, they're asking you, could this proposed reaction happen spontaneously? So in part A, we break out the reduction and the oxidation half reactions. So if copper, the metal, is turning into copper, the ion, the only thing that could be happening to that copper is the loss of electrons. And if hydrogen ion is turning into hydrogen gas, that's a classic reduction reaction. You're going to visualize that for yourself in a future lab where hydrogen gas would be bubbling off of the cathode. So by definition, the cathodic reaction was that the zero voltage, the one to which all other reduction reactions or half reactions were being compared. And notice that this time they actually wrote it as the copper solid metal being oxidized, but still on the right, they wrote its reduction potential as a positive 0.34. So the rule is take the cathode minus anode, and 0 minus a positive 0.34 is a negative 0.34. If, when you do cathode minus anode, you get a negative number, your only conclusion is that is not a spontaneous reaction as written. So my answer to A would be Based upon the fact I have a negative voltage, it is non-spontaneous. Now, before I leave this slide, let's just take a quick look at the second question because they don't show it on the next page. If chlorine, the element, is turning into chloride, the ions, they must be gaining electrons. So chlorine turning into chloride is the reduction, and iodide turning into iodine is the oxidation half reaction. So the next slide finishes up that first question. Could that reaction have been spontaneous? And of course not. If you have a negative cell potential, then the direction in which it's written on the piece of paper tells you that it's not spontaneous. This is just showing if you had flipped the whole thing around, you would have gotten a spontaneous reaction because the voltage would have been positive. But this is not what was written on the previous page. Now look at that second one, part B. We identified that the chlorine must be being reduced because that's the only way you can turn an element into an ion is by picking up extra electrons. Therefore, iodide turning into iodine must be the oxidation. Cathode minus anode. 1.36 minus 0.54 gives us a positive 0.82 volts. So predicting whether or not, as written on a piece of paper, a reaction is spontaneous or not is simply duplicating the processes that you've learned before. Voltage comes up positive, it's spontaneous. Negative, it's not. And on that note, I'm going to stop because probably our last or second to last podcast is connecting spontaneity to the flow of electrons. And we will stop at this point in time and pick up on the next podcast later.